Membership and coordination services. Projects like Zookeeper or ETCT are often described as distributed key-value stores or coordination and configuration services. The API of such a service looks pretty much like that of a database. You can read and write the value for a given key and iterate over keys. So if they're basically databases, why do they go to all the effort of implementing a consensus algorithm? What makes them different from any other kind of database? To understand this, it is helpful to briefly explore how a service like Zookeeper is used. As an application developer, you will rarely need to use Zookeeper directly, because it is actually not well suited as a general-purpose database. It is more likely that you will end up relying on it indirectly via some other project. For example, HBase, Hadoop Yarn, OpenStack Nova, and Kafka all rely on Zookeeper running in the background. What is it that these projects get from it? Zookeeper and ETCT are designed to hold small amounts of data that can fit entirely in memory, although they still write to disk for durability. So you wouldn't want to store all of your applications' data here. That small amount of data is replicated across all the nodes, using a fault-tolerant total order broadcast algorithm. As discussed previously, total order broadcast is just what you need for database replication. If each message represents a write to the database, applying the same rights in the same order keeps replicas consistent with each other. Zookeeper is modeled after Google's Chubby Lock service, implementing not only total order broadcast and hence consensus, but also an interesting set of other features that turn out to be particularly useful when building distributed systems. Linearizable atomic operations using an atomic compare and set operation. You can implement a lock. If several nodes concurrently try to perform the same operation, only one of them will succeed. The consensus protocol guarantees that the operation will be atomic and linearizable, even if a node fails or the network is interrupted at any point. A distributed lock is usually implemented as a lease, which has an expiry time so that it is eventually released in case the client fails. See process pauses on page 295. Total ordering of operations as discussed in the leader and the lock on page 301. When some resource is protected by a lock or lease, you need a fencing token to prevent clients from conflicting with each other in the case of a process pause. The fencing token is some number that monotonically increases every time the lock is acquired. Zookeeper provides this by totally ordering all operations and giving each operation a monotonically increasing transaction ID ZZ and version number C version. Failure detection. Clients maintain a long-lived session on Zookeeper servers, and client and server periodically exchange heartbeats to check that the other node is still alive. Even if the connection is temporarily interrupted or a Zookeeper node fails, the session remains active. However, if the heartbeats cease for a duration that is longer than the session timeout, Zookeeper declares the session to be dead. Any locks held by a session can be configured to be automatically released when the session times out. Zookeeper calls these ephemeral nodes change notifications. Not only can one client read locks and values that were created by another client, but it can also watch them for changes. Thus, a client can find out when another client joins the cluster based on the value it writes to Zookeeper, or if another client fails, because its session times out and its ephemeral nodes disappear. By subscribing to notifications, a client avoids having to frequently poll to find out about changes. Of these features, only the linearizable atomic operations really require consensus. However, it is the combination of these features that makes systems like Zookeeper so useful for distributed coordination. One example in which the Zookeeper/Chubby model works well is if you have several instances of a process or service, and one of them needs to be chosen as leader or primary. If the leader fails, one of the other nodes should take over. This is of course useful for single-leader databases, but it's also useful for job schedulers and similar stateful systems. Another example arises when you have some partitioned resource database, message streams, file storage, distributed actor system, etc., and need to decide which partition to assign to which node. As new nodes join the cluster, some of the partitions need to be moved from existing nodes to the new nodes in order to rebalance the load. See rebalancing partitions on page 209. As nodes are removed or fail, other nodes need to take over the failed node's work. These kinds of tasks can be achieved by judicious use of atomic operations, ephemeral nodes, and notifications in Zookeeper. If done correctly, this approach allows the application to automatically recover from faults without human intervention. It's not easy, despite the appearance of libraries such as Apache Curator that have sprung up to provide higher-level tools on top of the Zookeeper Client API, but it is still much better than attempting to implement the necessary consensus algorithms from scratch, which has a poor success record. An application may initially run only on a single node, but eventually may grow to thousands of nodes. Trying to perform majority votes over so many nodes would be terribly inefficient. Instead, Zookeeper runs on a fixed number of nodes, usually 3 or 5, and performs its majority votes among those nodes, while supporting a potentially large number of clients. Thus, Zookeeper provides a way of outsourcing some of the work of coordinating nodes consensus, operation ordering, and failure detection to an external service. Normally, the kind of data managed by Zookeeper is quite slow changing. It represents information like the node running on 10.1.1.23 is the leader for partition 7, which may change on a timescale of minutes or hours. It is not intended for storing the runtime state of the application, which may change thousands or even millions of times per second. If application state needs to be replicated from one node to another, other tools such as Apache Bookkeeper can be used. Zookeeper, ect, and console are also often used for service discovery, that is, to find out which IP address you need to connect to in order to reach a particular service. In cloud data center environments, where it is common for virtual machines to continually come and go, you often don't know the IP addresses of your services ahead of time. Instead, you can configure your services such that when they start up they register their network endpoints in a service registry, where they can then be found by other services. However, it is less clear whether service discovery actually requires consensus. DNS is the traditional way of looking up the IP address for a service name, and it uses multiple layers of caching to achieve good performance and availability. Reads from DNS are absolutely not linearizable, and it is usually not considered problematic if the results from a DNS query are a little stale. It is more important that DNS is reliably available and robust to network interruptions. Although service discovery does not require consensus, leader election does. Thus, if your consensus system already knows who the leader is, then it can make sense to also use that information to help other services discover who the leader is. For this purpose, some consensus systems support read-only caching replicas. These replicas asynchronously receive the log of all decisions of the consensus algorithm, but do not actively participate in voting. They are therefore able to serve read requests that do not need to be linearizable. Zookeeper and Friends can be seen as part of a long history of research into membership services, which goes back to the 1980s and has been important for building highly reliable systems, for example for air traffic control. A membership service determines which nodes are currently active and live members of a cluster. As we saw throughout Chapter 8, due to unbounded network delays it's not possible to reliably detect whether another node has failed. However, if you couple failure detection with consensus, nodes can come to an agreement about which nodes should be considered alive or not. It could still happen that a node is incorrectly declared dead by consensus, even though it is actually alive, but it is nevertheless very useful for a system to have agreement on which nodes constitute the current membership. For example, choosing a leader could mean simply choosing the lowest numbered among the current members, but this approach would not work if different nodes have divergent opinions on who the current members are. Summary. In this chapter we examined the topics of consistency and consensus from several different angles. We looked in depth at linearizability, a popular consistency model. Its goal is to make replicated data appear as though there were only a single copy, and to make all operations act on it atomically. Although linearizability is appealing, because it is easy to understand, it makes a database behave like a variable in a single-threaded program. It has the downside of being slow, especially in environments with large network delays. We also explored causality, which imposes an ordering on events in a system, what happened before what, based on cause and effect. Unlike linearizability, which puts all operations in a single, totally ordered timeline, causality provides us with a weaker consistency model. Some things can be concurrent, so the version history is like a timeline with branching and merging. Causal consistency does not have the coordination overhead of linearizability and is much less sensitive to network problems. However, even if we capture the causal ordering, for example using LAMP or timestamps, we saw that some things cannot be implemented this way. In timestamp ordering is not sufficient. On page 347 we considered the example of ensuring that a username is unique and rejecting concurrent registrations for the same username. If one node is going to accept a registration, It needs to somehow know that another node isn't concurrently in the process of registering the same name. This problem led us toward consensus. We saw that achieving consensus means deciding something in such a way that all nodes agree on what was decided, and such that the decision is irrevocable. With some digging, it turns out that a wide range of problems are actually reducible to consensus and are equivalent to each other in the sense that if you have a solution for one of them, you can easily transform it into a solution for one of the others. Such equivalent problems include linearizable compare and set registers. The register needs to atomically decide whether to set its value, based on whether its current value equals the parameter given in the operation. Atomic transaction commit. A database must decide whether to commit or abort a distributed transaction. Total order broadcast. The messaging system must decide on the order in which to deliver messages. Locks and leases. When several clients are racing to grab a lock or lease, the lock decides which one successfully acquired it. Membership/coordination service. Given a failure detector, for example timeouts, the system must decide which nodes are alive and which should be considered dead because their sessions timed out. Uniqueness constraint. When several transactions concurrently try to create conflicting records with the same key, the constraint must decide which one to allow and which should fail with a constraint violation. All of these are straightforward if you only have a single node, or if you are willing to assign the decision-making capability to a single node. This is what happens in a single leader database. All the power to make decisions is vested in the leader, which is why such databases are able to provide linearizable operations, uniqueness constraints, a totally ordered replication log, and more. However, if that single leader fails, or if a network interruption makes the leader unreachable, such a system becomes unable to make any progress. There are 3 ways of handling that situation. Wait for the leader to recover, and accept that the system will be blocked in the meantime. Many XA/ATA transaction coordinators choose this option. This approach does not fully solve consensus because it does not satisfy the termination property. If the leader does not recover, the system can be blocked forever. Manually fail over by getting humans to choose a new leader node and reconfigure the system to use it. Many relational databases take this approach. It is a kind of consensus by act of God. The human operator, outside of the computer system, makes the decision. The speed of failover is limited by the speed at which humans can act, which is generally slower than computers. Use an algorithm to automatically choose a new leader. This approach requires a consensus algorithm, and it is advisable to use a proven algorithm that correctly handles adverse network conditions. Although a single leader database can provide linearizability without executing a consensus algorithm on every write, it still requires consensus to maintain its leadership and for leadership changes. Thus, in some sense, having a leader only kicks the can down the road. Consensus is still required, only in a different place and less frequently. The good news is that fault-tolerant algorithms and systems for consensus exist, and we briefly discussed them in this chapter. Tools like Zookeeper play an important role in providing an outsourced consensus, failure detection, and membership service that applications can use. It's not easy to use, but it is much better than trying to develop your own algorithms that can withstand all the problems discussed in Chapter 8. If you find yourself wanting to do one of those things that is reducible to consensus, and you want it to be fault-tolerant, then it is advisable to use something like Zookeeper. Nevertheless, not every system necessarily requires consensus. For example, leaderless and multi-leader replication systems typically do not use global consensus. The conflicts that occur in these systems, see handling write conflicts on page 171, are a consequence of not having consensus across different leaders. But maybe that's okay. Maybe we simply need to cope without linearizability and learn to work better with data that has branching and merging version histories. This chapter referenced a large body of research on the theory of distributed systems. Although the theoretical papers and proofs are not always easy to understand, and sometimes make unrealistic assumptions, they are incredibly valuable for informing practical work in this field. They help us reason about what can and cannot be done, and help us find the counterintuitive ways in which distributed systems are often flawed. If you have the time, the references are well worth exploring. This brings us to the end of Part Roman 2 of this book, in which we covered Replication Chapter 5, Partitioning Chapter 6, Transactions Chapter 7, Distributed System, Failure Models Chapter 8, and finally Consistency and Consensus Chapter 9. Now that we have laid a firm foundation of theory, in Part Roman 3 we will turn once again to more practical systems and discuss how to build powerful applications from heterogeneous building blocks. Prince Mahajan, Lorenzo Alvasi, and Mike Dallin. Consistency, availability, and convergence. University of Texas at Austin, Department of Computer Science. Tech Report UTXTR 11-22, May 2011. Alex Scotti. Adventures in Building Your Own Database at All Your Base, November 2015. David K. Gifford. Information Storage in a Decentralized Computer System, Xerox Palo Alto Research Centers, CSL 81-8. June 1981. Mike Burrows. The Chubby Lock Service for Loosely Coupled Distributed Systems, at 7th Usenix Symposium on Operating System Design and Implementation OSTI, November 2006. EDC 2.0.12 Documentation, Core OS, Inc. 2015. Apache Curator, Apache Software Foundation, curator.apache.org, 2015. Nicholas Ekstrom, Mikhail Panchenko and Jonathan Ellis. Possible issue with read repair? Email thread on Cassandra Dev mailing list, October 2012. Paul R. Johnson and Robert H. Thomas, RFC 677. The Maintenance of Duplicate Databases, Network Working Group, January 27, 1975. Bruce G. Lindsay, Patricia Griffiths Sellinger, C. Galtieri, et al. Notes on Distributed Databases, IBM Research. Research Report RJ 2571 33471, July 1979. Eric A. Brewer. NoSQL, Past, Present, Future, at QCon San Francisco, November 2012. Adrian Cockcroft. Migrating to Microservices at QCon London, March 2014. Martin Kleppmann. A Critique of the CAP Theorem, RZIV 1509.05393, September 17. 2015. Thompson. Memory Barriers/Fences, mechanicalsympathy.blogspot.co.uk, July 24, 2011. Wyatt Lloyd, Michael J. Friedman, Michael Kaminsky, and David G. Anderson. Stronger Semantics for Low Latency, Geo-Replicated Storage, at 10th Usenix Symposium on Networked Systems Design and Implementation NSEI, April 2013. Marek Zaworski, Annette Bayinosa, Walter Bailgas, et al. Swift Cloud. Fault-tolerant geo-replication integrated all the way to the client machine. INRIA Research Report 8347, August 2013. Philippe Adjou, Nathan Bronson, Sanjeev Kumar, et al. Challenges to Adopting Stronger Consistency at Scale, at 15th Usenix Workshop on Hot Topics in Operating Systems Hot OS, May 2015. Peter Bayles. Causality is Expensive and What to Do About It. Bayles.org, February 5, 2014. Mahesh Balakrishnan, Dalila Malkai, Vijayan Prabhakaran, et al. Corfu. A Shared Log Design for Flash Clusters, at 9th Usenix Symposium on Networked Systems Design and Implementation NSDI, April 2012. Robert Van Rennes and Fred B. Tnader. Chain Replication, for Supporting High Throughput and Availability, at 6th Usenix Symposium on Operating System Design and Implementation OSTI, December 2004. Thenamalayan Sankaranarayana Pillai, Vijay Chidambaram, Ramnath and Aligapan, et al. All file systems are not created equal. On the Complexity of Crafting Crash-Consistent Applications, at 11th Usenix Symposium on Operating Systems Design and Implementation OSTI, October 2014. Understanding Transactionality in Azure, N-Service Bus Documentation, Particular Software, 2015. In Doubts Act Resolution Server Configuration Option, SQL Server 2016 Documentation, Microsoft, Inc., 2016. Barbara H. Liskov and James Cowling. View Stamped Replication, Revisited, Massachusetts Institute of Technology, Tech Report MITC CLTR 2012-021, July 2012. Diego Ungaro, Consensus, Bridging Theory and Practice, PhD Thesis, Stanford University, August 2014. Andrei Medeiros, Zookeeper's Atomic Broadcast Protocol, Theory and Practice, Aalto University School of Science, March 20, 2012.